Hi, welcome to the first in the Teacher's Guide series for Polyup. First, let's introduce Poly, your AI sidekick. Poly is well versed in all sorts of mathematical and computational knowledge. Poly will act as a guide and companion as players go through the puzzles in Polyup. Unfortunately, most of Poly's memory was lost in a short circuit, so it's up to the player to restore Poly's memory by solving problems and learning computational thinking. Polyup uses a functional, stack-based, reverse Polish notation block programming language for calculation and computation. That was a mouthful. I'll explain what that all means by the end of this video, but let's give you a quick overview first. There are two types of blocks that you'll be seeing most often. Square blocks are operators, and circle blocks are numbers or other values. Most square blocks take the two circles above them as inputs and produce a single circle as the output. This video will cover 5 topics about Polyup and the Polyscript language. First, we'll cover the basic building blocks of the language. Next, we'll explain how the reverse Polish notation order of operations works. After that, we'll cover variables and stacks, and finish up with a few examples of simple loops and iterations. Let's take a look at the main user interface in Polyup. The 4 vertical lines here are called stacks. They're empty at the moment, but we'll have a chance to fill them up soon enough. The buttons at the bottom of the screen open up palettes full of blocks that you can put in your program. In this case, you can drag the numbers directly out into the program, or you can tap on a few of them to enter more digits, and then drag the new block out of the box at the top. The green button brings up a palette full of mathematical operators, plus a couple of familiar constants. After you drag and drop the blocks you want into your program, tap on Poly to open the runtime screen, then hit the play button to start. The program will read from the top down, applying any operators to the numbers above them, until it reaches the bottom for the final result. This program added 5 and 2 to get a 7. For another example, we can change the plus block to a minus, in which case it will subtract 2 from 5 and give you a 3. Now you might be asking what happens if you use more than one operator. How does Polyup determine the order in which to apply the operators? Polyup uses what is known as reverse Polish notation, or postfix notation. The operators are always placed immediately after their operands. Thus 3, 4 plus becomes 7. This single rule is a lot simpler than the common order of operations in infix notation, which you might remember as parentheses, exponentiation, multiplication and division, and addition and subtraction, or PEMDAS. RPN can be a little harder to read though, since operators might be pretty far away from the operands they're working on. For a concrete example, this infix expression takes the expression 1 plus 2, multiplies it by 4, and then adds that expression to 5 and subtracts 3 from the result. An equivalent expression in reverse Polish notation would look like this. Reading from left to right, you add 1 and 2, multiply the result by 4, and add the multiplication's result to 5, and subtract 3 from the result of the addition. Note that you never need parentheses in RPN, since there's no ambiguity as to what values an operator should operate on. In Polyup, this expression looks the same, only read from top to bottom instead of left to right. The program will pass over any numbers and apply each operator to the numbers immediately preceding it, replacing the operator with its result. Watch out though, operators without enough arguments will produce an error. Here's a quick example of the program in action. After we pass over the 3 numbers, we apply plus to the 5 and 6, producing an 11, and then apply the second plus to the 3 and 11 to get 14. We can get the same result with these blocks in a slightly different order. Here we're adding the 3 and 5 first to get 8, and then adding the 8 and 6 to get 14. Even if you have more than one different operator to work with, there are often still multiple ways to write an expression to get the same result. In this case, 5 plus 6 is 11, and 11 minus 3 is 8. Or 5 minus 3 is 2, and 6 plus 2 is 8. Or 5 minus 3 is 2, and 6 plus 2 is 8. In some cases, though, changing the order of your operators will change the result of the expression. Here we first add 1 plus 1 to get 2, and then subtract 1 to get 1. In this example, however, even though we're adding 1 and 1 first to get a 2, we're then subtracting the result from 1 instead of subtracting 1 from the result, which gives us -1. The next block types you will encounter in Polyup are the variable assignment and recall blocks. Assignment blocks are red squares with an arrow pointing to the variable name, and recall blocks are red circles. Assignment blocks behave a bit like operators, but they take one input and don't produce any output. Recall blocks, like other circle blocks, simply store a value and turn into that value when the program reaches them. In this simple example, the assignment block stores 5 in the variable x, and then the recall block turns back into the 5. One of the main applications for a variable is to use a single value more than once. In this program, we take a single value and multiply it by itself to square the number. First, the assignment block stores the value 5 in the variable x. Then the recall blocks replace themselves with the current value of x. And finally, we multiply the 5's together to get 25. There are 6 different variables to use by default, although it's rare that you'll need to use more than 2 or 3 at once. When assigning to multiple variables at once, remember that the consecutive assignment blocks will take their inputs in reverse order of the blocks being assigned to them. Here we assign the 5 to x, the 6 to y, and then recall the variables again to subtract them and get 1. If we switch the order of the assignment blocks or the recall blocks, we can use these variables to switch the 6 and 5 around and subtract 6 from 5 to get -1. This is the only general purpose way to swap two blocks if a puzzle locks them in place. You may have noticed that there are 4 stacks on the programming screen, but we've only been using the leftmost one so far. This section will explain how to put the others to work. If you drag your finger from one of the symbols below the other stacks, you'll pick up a yellow circle with that stack's symbol on it. I won't go into detail on what this means right now, but I'll mention that, like any other circle, it represents a value rather than an operation. If you use your finger to hold the yellow circle in place for a second or two, it will start growing, and then flip to make an orange diamond. Orange diamonds are blocks that run the program contained in a stack. Now let's work over a simple example. This program might look pretty familiar. Like one of the examples from the variables section, it takes a number and squares it. When we run the program, it passes over the 6, but when it reaches the diamond block, the diamond replaces itself with the contents of the second stack, and the program begins executing from the top of that stack. As before, the assignment block takes the number, and then we recall it twice and multiply to find the number's square. Importantly, even though the stack 2 didn't have any number to assign to x, the 6 from stack 1 carried over when we started stack 2. You can chain several functions in a row to save a lot of space in your program and produce very interesting results. Here we're using the same square function as the last example, but instead of using it just once, we're squaring 6 3 times in a row. As before, the function block expands into the function's code and uses the 6 as input. But now we square 36 to get 1296, and square that to get, well, a rather large number. Here are a few ideas for some functions you could write yourself or ask your students to create. We have a function with 1 input and 1 output, a couple of functions with 3 inputs and 1 output, a function with 1 input and 2 outputs, and a function with 2 inputs and 2 outputs. So far, we've looked at writing functions and using them in another stack to create operator-like behavior, but you can also make a function call itself to create a loop. The simplest example of a loop is an infinite loop, which this section will cover. So what if we want to make a program that keeps counting until the end of time? We can make a function that adds 1 to its input and then loops. Note that we need to give it a number to start counting from, which is where the 1 on the left side comes in. The first call to the function will use that 1 as an input, add 1 to it, and then repeat, but now with 2 as an input. This will keep going as long as you let it. If we make the function multiply the input by 2 instead, we'll get a series of ever-increasing powers of 2. With a different starting point, our infinite loops can produce completely different series. If we take a 1 and add 2 forever, we'll get the odd natural numbers, while if we start with a 2, we'll get the evens instead. So far, all our infinite loops have had one input and one output, so they just work in place. But here we have a function with one input and two outputs. The input is the number to square, and the outputs are the square of that number and the next number to square. So when we run it, the sequence of squares will expand upward as the loop continues. This is equivalent to calculating 1 squared, then 2 squared, then 3 squared, then 4 squared, and so on. The next loop is a bit more complicated. It is using two different stacks to loop back and forth to each other. Stack 2 has two inputs, the nth triangular number and n. Its output is the n plus 1th triangular number. Stack 3 has one input and three outputs. The input is the n plus 1th triangular number, and the output is two copies of that number and n plus 1. Note that stack 3 remembers the value of x from stack 2. When we run this loop with the initial conditions of 1, 1, 1, we get 1, 3, 6, 10, and so on. Triangular numbers, by the way, are defined such that Tn is equal to the sum of all integers between 1 and n inclusive, or alternatively, Tn is Tn minus 1 plus n. Here we have another loop that produces a sequence of numbers. The inputs are the sum of all odd numbers up to n and n itself, and the outputs are two copies of that sum plus the next odd number, as well as a copy of the next odd number. Running this loop will give us a familiar sequence. Why is that? If we split a square into layers, you can see that each layer contains two more dots than the previous one. So if we start with 1 and add each new layer to the previous ones, we get the sequence of square numbers. So far, all the examples here have been of divergent series. The numbers keep getting farther and farther away from where you started. Here's an example, though, of a convergent series. It will keep getting closer and closer to a fixed point. It may take infinitely long to actually reach that point, but even after just a few iterations, it's only off by 0.4%. What's the actual meaning of this function, though? In this case, we want to find what is called a fixed point of a function, that is to say, a value at which f of x is equal to x. We'll first make a guess at what the fixed point is, then use that guess as the input to the function. We use the result as the next guess. If the series converges, then we've found a fixed point. Applying this method to the function f of x equals 0.5x plus 0.5, we get this series. Graphing this out sort of gives us a staircase shape. We go vertically to fxi, then horizontally to xi plus 1, and so on. In this case, the fixed point is at x equals 1 and y equals 1. Here are some workshop ideas. Try using this method to find the fixed point of other functions. Can you come up with rules for what sort of functions this method works on? Also try different guesses as well as different functions. Are there functions for which some guesses converge and others diverge? You might be familiar with Newton's method for approximating the square root of a number. Like the previous example, this is a set of rules to apply iteratively to find the fixed point of a function. You make a guess, compare it with the value of the function at that point, and use that to improve your guess. The rules for improving it are a bit different in this case, though. If we're trying to find the square root of 4, what happens if we apply these rules repeatedly with an initial guess of 2? Here's a program that uses an infinite loop to find the square root of 4 from an initial guess of 1.5. You'll find that it very quickly converges on the right answer. Some more workshop ideas might be change the guess and see if you can find any that give you a divergent result, or maybe even a different convergence point. Or change the value of x to find the square root of a different number. Thank you for watching the first Teacher's Guide video. Keep an eye on Polyup.com for more videos in the coming weeks, or sign up for the Hour of Mod event to subscribe to our newsletter. See you soon!